The topic of the video is linear harmonic oscillator using Schrodinger's wave method. Schrodinger's wave equation solution method. A particle of mass m that's attached to a spring of spring constant k and executing the periodic motion in one dimension is called a linear harmonic oscillator, as shown in this figure here. The restoring force acting on the particle can be taken as that of Hooke's law, like this. The Newton's equation of motion for this particle can be written as this, and then if you equate, if you write instead of a as a d square x by dt square, and if you equate that to minus kx, and if you neglect the vectorial nature of x, we can get this second order differential equation. And here if you call omega sub c is equals to k by m, we get this as the differential equation. And if you take the solution for x of this type, uh, when we substitute this into this equation and solve, we get omega is equals to plus or minus omega c. And if you put the initial condition at t is equals to 0, x is equals to 0, then we get x is equals to x naught into sine omega c t. Therefore the period of x is actually the angular frequency of oscillation of x is actually our omega c. So we can write angular frequency of this harmonic oscillator is square root k by m, and then the linear frequency is 1 by 2 pi of that. And since we use this fact in future, we'll call this omega c expression as equation number 1. The total energy of the linear linear harmonic oscillator can be written as a summation of its kinetic energy and potential energy, and kinetic energy will be having half mv squared, and then v is equals to dx by dt. So we'll be getting the derivative of sine will give you, will make it cos, so we'll be getting cos square omega c squared, and then omega c squared factor coming here. And the potential energy of the linear harmonic oscillator can be written as integration some reference point 0 to x into f dot dx. And if you put f is equals to minus kx and then do the integration, we get half kx square for this potential energy. And if you substitute x is equals to x naught into sine square, sine omega t, we'll get this factor here. And if you use the fact that omega c squared into m is equals to k from equation number 1, we get this expression for our potential energy. And if you take the summation of both kinetic and potential energies, we'll get this expression for the total energy of linear harmonic oscillator. And here these m and omega c's are constants, but this x naught can be taking any possible value. So the energy of linear harmonic oscillator is continuous in classical picture. But if the particle size is very tiny, then we should be solving this problem using quantum mechanical Schrodinger equation, which is this equation number 2. And here the h is taken as kinetic energy operator and potential energy operator together, and this is actually our Hamiltonian operator. As momentum operator is minus ih cut into dou by dou x, we can even write h operator like this. And since this h is independent of time, we can assume a solution for psi xt as this equation number 3. And if we substitute this into the Schrodinger equation, which was equation number 2, then we end up with h phi is equals to e phi. And if we substitute h expression here, we'll get this equation. And since this phi x is only a function of x, we can even replace dou square by dou x square with d square by dx square. And if you do that, we get the Schrodinger equation as shown in equation number 4. And if you take a new variable which is xi equal to alpha into x, then we can say d xi is equals to alpha into dx, and then xi square is equal to alpha square into x square, and d xi square is equals to alpha square into dx square. So in place of dx square we should be substituting d xi square by alpha square. And if you substitute all these things, I mean the relevant things, in equation number 4, then the equation can be recast in terms of xi's like this. And here the alpha square gonna go up. And then if you want to have only d square phi by dz square in the first term, then we can get this equation looking like this with a bracket here in the second term. We choose alpha square such that the second term in the bracket here, that is this one, is equals to 1 into xi square. That means this entire thing here should be equal to 1. And then if you put that way, then alpha power 4 is equals to this, or alpha square is equals to square root of mk over h cut square. And we call the first term in the bracket, which is 2me over h cut square, and alpha square is equals to alpha lambda, and then that gives you lambda is equals to this if you substitute for alpha squared. And if we cancel out m factor here, we'll get lambda is equals to 2e by h cut into that square root m by k. And then if you use the fact that omega c is equals to square root of k by m, we'll get the expression for lambda as shown in equation number 5. Then the Schrodinger equation will look like that shown in equation number 6. And we can take a solution for xi as h function of xi into exponential minus of xi squared. And since the equation requires you to have d square phi by d xi square, we try to find out that. And if you do d phi by dz, we can use uv formula on the right hand side. So if you keep h constant, and if you do differentiation for this, we get this. And then we keep the exponential term constant, and then if you do the differentiation of h, we'll get h prime here. So if you write those terms together with common factor of exponential, we'll get h prime minus si into this exponential for d phi by d psi. And if you do the differentiation of this one more time, we get d square phi by d xi square is equals to this factor here. And simplification will make it look like this. After substitution of this d square phi by dz square, the equation number 6, which was our Schrodinger equation, will look like the equation number 7. Of course, here we have cancelled this xi square into h here and here, so it will get the equation number 7. And if you take h as a power series summation as a naught into xi power s plus a1 into xi power s plus 1, etc., then its first derivative h prime will give you this expression, and the second derivative will give you this expression. And if we substituted h prime and h double prime in equation number 7, we'll be getting this big bigger thing here, setting up to 0. And if you compare the xi power s minus 2 terms on both sides, we can say that it is appearing here. So this a naught into s into s minus 1 is equals to 0. And if you compare xi power s minus 1 terms on both sides, which is coming here, so a1 into s plus 1 is equals to 0. And if you compare xi power s, which is coming here, here and here, we will get this expression. And if you write e naught terms together here, we can actually write this as this. And if you compare xi power s plus 1 terms on both sides, and we can say that they are coming, xi power s plus 1 terms are coming here, and then here, and then here. So we get this expression. And then if you write a1 as common factor, we can take this thing in bracket. And if you compare the xi power s plus 2 terms on both sides, we can actually set this thing up equal to 0. And if you write a2 as a common factor, we can get this one. By observing all these equations, like for a4 relating to a2, a3 relating to a1, we can write a recursion relationship as s plus l plus 1 into s plus l plus 2 into a sub l plus 2 minus this factor into al, I mean a sub l is equals to 0, as a recursion relationship for different values of L, that is 0, 1, 2, 3, etc. We'll be able to get all these equations that we had earlier for A2s, A4s, etc. And if you want to have the power series of H terminating at L plus Lth coefficient, we should be having A sub L plus 2 is equals to 0. And if it should be that way, then we should be having this numerator should be equal to 0. That is this expression. And here if you call s plus l as an integer n, then we can get lambda is equals to 2n plus 1. And if you recall from equation number 5 that lambda was 2e by h cut omega c, we can actually invert or we can equate those two equations, and we can get expression for energy E as n plus of into h cut omega c. So we can even put a subscript here as n, and we call this as equation number 8. And this is the energy of harmonic oscillator in quantum mechanics. Therefore, we can say that energy of linear harmonic oscillator is quantized in quantum mechanics. And the equation number 7, which was a differential equation for H, says that it's actually polynomial equation, I mean Hermite differential polynomial equation. So we can call these even H or Hermite polynomials H sub n as a function of xi. So we can take our wave function phi of xi as some kind of normalization factor, which is n capital N sub n and then h sub n into xi, and exponential factor like this, and we can call this as equation number 9. And if you want to know a bit about these Hermite polynomials, they can be generated by this equation here, that is h sub n xi is equals to minus 1 power n into e power xi square into dou n over dou xi power n, and then exponential minus xi square. And if you put n is equals to 0, we'll be getting h0 xi is equals to 1. And if you put n is equal to 1, we'll be getting it is equals to dou 2 xi. And if you put n is equals to 2, we'll be getting 4 xi square minus 2. Of course, we'll be doing these partial differentials each time in h1 and then 2 times in h2. And then these polynomials also have got these normalization condition through this integral, and then we may call this as equation number 10 because we'll use this in the future. And they also are orthogonal to each other. That means if you take two different Hermite polynomials and then the integral will make it to 0. If the wave function is actually normalized, then we should be having this integral of phi x star into phi x dx is equals to 1. But if you recast this integral in terms of xi's, then we can write phi xi here and phi xi here, and here dx can be written as d xi over alpha. So we get n sub n squared over alpha into this integral, and it should be equal to 1 because we want it to be normalized. But from the equation number 10, this integral's value is given by square root of pi into 2 power n into n factorial, and it should be equal to 1. So from this expression we get n sub n is equals to this factor here, and if you use this into the wave equation, I mean wave functions equation, we can write phi of xi is equals to this. Or if we express this in terms of even x in place of xi, then we can write this expression and call that as equation number 11. So the equation number 8, which was for energy, and then equation number 11, which is for the wave function of linear harmonic oscillator, are actually the things for quantum mechanical uh, harmonic oscillator. For n is equals to 0, we can write the wave function like this, and if you use the h0 thing, I mean value that we had in the earlier page, we can get this expression for wave function, and energy is given by this. And for n is equal to 1, we can have the wave function looking like this, and energy is given by this. And for n is equal to 2, we'll have wave function looking like this, and the energy looking like this. And we can even prepare a kind of a energy level diagram for this, where this potential energy of kx square will be looking like this parabola, and we can have energy ground state energy, which is E0, and then with wave function phi 0, and the second level E1 and phi 1, E2 with wave function phi 2, and the ladder may go up, but the spacing here will be actually same for I mean between any consecutive levels.